Hi there. So we had previously shown that Albert Einstein had interpreted the photoelectric effect as indicating that electromagnetic radiation behaved or had particle-like behavior. So this was in addition to the obviously wave-like behavior that had previously been exhibited by electromagnetic radiation, and previous to Einstein's theories had been considered to be just wave-like. Now, Louis de Broglie, who we show on the right here, was a PhD student, and he came up with the rather amazing idea that not only did electromagnetic radiation exhibit wave-like and particle-like characteristics, but he also proposed that moving particles, which have obvious particle-like behavior, also exhibited wave-like characteristics. Now, to try to understand his reasoning, it's best to go back to the equation we had left off with on the photoelectric effect presentation, where we had shown that you have this momentum, if you like, for a photon as being equal to Planck's constant divided by lambda. Now, C here is the momentum of the electromagnetic radiation, and we know from Planck and Einstein that this electromagnetic radiation, that this is the velocity, or you can consider this as the velocity of the actual photons of energy, h nu. So what de Broglie's fairly, well, easy now, but obviously a great insight, showed that if you now have any moving particle with velocity v, you can write a very similar equation in the sense that mv is equal to h over lambda. So these are usually, our usual symbol is small p for momentum, so p, the momentum of any moving particle, is Planck's constant divided by its wavelength, or lambda is equal to h over p. So essentially, de Broglie here extended this wave-particle duality that Einstein had proposed for energy, electromagnetic radiation, to all moving particles. And at this time, this is just a postulate, as I indicate here, theoretical postulate, but it was shown, and it's quite not that difficult to show, that electrons have indeed particle-like activities. And the classic behavior exhibited by waves, of course, is diffraction. And if we move down here, we can show, here we have on the left, we have the diffraction pattern made by a beam of X-rays, electromagnetic radiation, passing through an aluminium foil, and you can see there's a diffraction pattern, nice diffraction pattern given. But on the right, the diffraction pattern here, in a nice pattern, is made by a beam of electrons passing through the exact same foil. So here, the electromagnetic radiation in the X-ray region is exhibiting diffraction properties, exhibiting wave-like properties, but you can see here on the right that the electron beam is exhibiting the exact same wave-like behavior. So this is, if you like, experimental proof of the de Broglie theory. So let's move on now to just do a few calculations or examples on this de Broglie theory. So if we take let's say we have a typical particle object that we're familiar with, so we have a tennis ball, and let's suppose the mass of the tennis ball is 50, let's say it's 57 grams, and its velocity, say it's 80 kilometers per hour. So you could be asked the question, what is the Broglie wavelength? What is lambda? So according to the Broglie, lambda is equal to h over the momentum, mass times velocity. So we put in our value for Planck's constant is 6.626 by 10 to the minus 34, and that's joules second. We divide that by the mass of the tennis ball, which is 57, and we like to keep our units in SI units, so I'm going to convert this to kilograms. So you multiply by 10 to the minus 3, that gives it in kilograms, and then you multiply by, and we need to keep it in meters per second, so it's 80 kilometers per hour, so that's 80 by 10 to the 3 meters, and then you divide that by 60 to bring it to minutes per minute, and you divide it by another 60 to bring it per second. So that'll give it to you your velocity in meters per second, which is the SI unit you want. And if you plug that values in, you should get a value of 5.2 by 10 to the minus 34 meters. Now what you can see immediately is that this value here, 10 to the minus 34 meters, is negligible compared with, say, the size of a tennis ball. So what that means is that every moving particle does have wave-like characteristics, but for everyday objects like a tennis ball, a moving tennis ball, the wavelength is so small that it's negligible and it can be completely neglected. And sorry to say, it doesn't have any effect on how well you serve. Let's take another, and this would take a typical example of an electron. And now let's say a typical velocity for the electron of, say, 1.0 by 10 to the 7 meters second minus 1. And you could again ask the question, what is the wavelength of that? So we again use the Broglie relationship. We said that lambda is equal to h over mass by the velocity. So it's again Planck's constant 6.626 by 10 to the minus 34 joules second, divided by, now we have the mass of the electron, 9.11 by 10 to the minus 31. That's in kilograms. We can find that from tables. And now we have to multiply that below the line by 1.0 by 10 to the 7. And again, that's our units, meters to seconds minus meters per second. And if we plug that in, we get 7.3 by 10 to the minus 11. Sorry, let's get that out there. 10 to the minus 11, and that's in meters. So I'm going to express that 7.3 by 10 to the minus 11 meters. That's equal to 0.73 by 10 to the minus 10 meters. And 10 to the minus 10 meters we know is better as 0.73 angstroms. So what you can see here now is that the wavelength of the electron, is in the region of the kind of distance that an electron is moving in an atom. So now the wavelength of this moving object is about the same, if you like, of the region in which it's moving. So now the wave-like properties are going to become significant, and it's going to exhibit properties like diffraction and so forth. So for the larger objects, practical objects that we meet in everyday life, they've all got this wave-like characteristics, but because the wavelength is so small, it's not detectable. But for something like an electron, which exists inside atoms and molecules, then the region in which it's confined to is similar to its wavelength, so therefore the wavelength properties become extremely important.